Alright, so we're here in the Pilot's Handbook of Aeronautical Knowledge. We're in Chapter 4, 4-19. This will be Aerodynamic Forces and Flight Maneuvers. This is forces and turns. Alright. If an aircraft were viewed in a straight and level flight from the front, and if the forces acting on the aircraft could be seen, lift and weight would be apparent. Two forces. If the aircraft were in a bank, it would be apparent that lift did not act directly opposite to the weight, rather it now acts in the direction of the bank. A basic truth about turns: when the aircraft bank, lift acts inward toward the center of the turn as well as upward. Newton's first law of motion, the law of inertia, states that an object at rest or moving in a straight line remains at rest or continues to move in a straight line until acted on by some other force. An aircraft, like any moving object, requires a sideward force to make it turn. In a normal turn, this force is supplied by banking the aircraft so that the lift is exerted inward as well as upward. The force of lift during a turn is separated into two components at right angles to each other. One component, which acts vertically and opposite to the weight, gravity, is called the vertical component of lift. The other, which acts horizontally toward the center of the turn, is called the horizontal component of lift, or the centripetal force. The horizontal component of lift is the force that pulls the aircraft from a straight flight path to make it turn. Centrifugal force is the equal and opposite reaction of the aircraft to change in direction and act equal and opposite to the horizontal component of lift. This explains why, in a correctly executed turn, the force that turns the aircraft is not supplied by the rudder. The rudder is used to correct any deviation between the straight track of the nose and the tail of the aircraft. A good turn is one in which the nose and tail of the aircraft track along the same path. If no rudder is used in a turn, the nose of the aircraft yaws to the outside of the turn. The rudder is used to bring the nose back in line with the relative wind. An aircraft is not steered like a boat or an automobile. In order for an aircraft to turn, it must be banked. If it is not banked, there is no force available to cause it to deviate from a straight flight path. Conversely, when an aircraft is banked, it turns, provided it is not slipping to the inside of the turn. Good directional control is based on the fact that the aircraft attempts to turn whenever it is banked. Pilots should keep this fact in mind when attempting to hold the aircraft in straight and level flight. Merely banking the aircraft into a turn produces no change in the total amount of lift developed. Since the lift during the bank is divided into vertical and horizontal components, the amount of lift opposing gravity and supporting the aircraft's weight is reduced. Consequently, the aircraft loses altitude unless additional lift is created. This is done by increasing the angle of attack until the vertical component of lift is again equal to the weight. Since the vertical component of lift decreases as the bangle increases, the angle of attack must be progressively increased to produce sufficient vertical lift to support the aircraft's weight. An important fact for pilots to remember when making constant altitude turns is that the vertical component of lift must be equal to the weight to maintain altitude. At a given airspeed, the rate at which an aircraft turns depends upon the magnitude of the horizontal component of lift. It is found that the horizontal component of lift is proportional to the angle of a bank. That is, it increases or decreases respectively as the angle of bank increases or decreases. As the angle of bank is increased, the horizontal component of lift increases, thereby increasing the ROT. Consequently, at any given airspeed, the ROT can be controlled by adjusting the angle of bank. Great. ROT. Did we already go over the ROT? Rate of turn. Rate of turn. To provide a vertical component of lift sufficient to hold altitude in a level turn, an increase in angle of attack is required. Since the drag of the airfoil is directly proportional to its angle of attack, induced drag increases as lift is increased. This in turn causes a loss of airspeed in proportion to the angle of bank. A small angle of bank results in a small reduction in airspeed, while a large angle of bank results in a large reduction in airspeed. Additional thrust power must be applied to prevent a reduction in airspeed in level turns. The required amount of additional thrust is proportional to the angle of bank. To compensate for added lift, which would result if the airspeed were increased during a turn, the angle of attack must be decreased or the angle of bank increased if constant attitude is to be maintained. If the angle of bank is held constant and the angle of attack decreased, the ROT, the rate of turn, decreases. In order to maintain a constant rate of turn as the airspeed is increased, the angle of attack must remain constant and the angle of bank increased. An increase in airspeed results in an increase of the turn radius, and centrifugal force is directly proportional to the radius of the turn. In a correctly executed turn, the horizontal component of lift must be exactly equal and opposite to the centrifugal force. As the airspeed is increased in a constant rate level turn, the radius of the turn increases. This increase in the radius of the turn causes an increase in the centrifugal force, which must be balanced by an increase in the horizontal component of lift, which can only be increased by increasing the angle of bank. In a slipping turn, the aircraft is not turning at the rate appropriate to the bank being used, since the aircraft is yawed toward the outside of the turning flight path. The aircraft is banked too much for the rate of turn, so the horizontal lift component is greater than the centrifugal force. Equilibrium between the horizontal lift component and the centrifugal force is reestablished by either decreasing the bank, increasing the rate of turn, or a combination of these two changes. A skidding turn results from an excess of centrifugal force over the horizontal lift component, pulling the aircraft toward the outside of the turn. The rate of turn is too great for the angle of bank. Correction of a skidding turn thus involves a reduction in the rate of turn, an increase in bank, or a combination of the two changes. To maintain a given rate of turn, the angle of bank must be varied with airspeed. This becomes particularly important in high-speed aircraft. For instance, at 400 miles per hour, an aircraft must be banked approximately 44 degrees to execute a standard rate turn, 3 degrees per second. At this angle of bank, only about 79% of the lift of the aircraft compromises the vertical component of the lift. This causes a loss of altitude until the angle of attack is increased sufficiently to compensate for the loss of the vertical lift. Alright, let's look at a picture. Alright, so normal turn, centrifugal force is equals horizontal lift. That's a good one. Slipping turn. Yeah, it's not going straight down anymore. Now it's going back that way a little bit. The load. And a skidding turn. Alright, so we're going to hold off there. That was 419 and 420. Aerodynamic forces and flight maneuvers, forces and turns. Alright, see ya.